Now, axisymmetric flow. Now, here in the definition itself, we can understand that symmetric means what? Same flow through the axis. Axis means it is a line, or we can say axis here, line, axis. Okay. So here the flow pattern is said to be axisymmetric if it is identical, means same along the plane, passes through the certain line, or else line means we can say it is axis. Okay. Now, why we are explaining here this axisymmetric flow? Because in the axisymmetric flow, the flow variables, whatever we are using, velocity, pressure, these two or these flow variables does not depends upon the angular velocity. Angular means the rotating. Okay. Angular velocity, angular coordinate theta means the velocity variables and velocity and the pressure and the remaining variables does not depends upon the angular coordinate theta. Means if you take the derivative of this v and p with respect to theta, that gives the answer 0. Okay, so this is a very important point here. Okay, so this also will include in our modeling the problem. Now let us come to the introduction of my problem. Now first of all, let us see the basic equations in the vector form. Now any analysis of the motion of the fluid which involves the governing equations, okay, which is in the form of non-linear partial differential equations, and these equations are called the primary equations of the fluid dynamics. So that we are going to derive in this in our model, in our problem. So what are the basic equations which are involved in our problem here? And those equations are called governing equations. Now the first one is the equation of continuity. Then next one is the equation of motion. What is the equation of continuity? It is dou rho by dou t plus del dot rho u bar equal to 0. Now the dot product of these two, which gives u bar dot del rho plus rho into del dot u bar equal to 0. Now from the first two terms, we can write it as a dou by d by dt of rho. Means what is d by dt is nothing but d by dt is nothing but by combination of these two, by combining these two, we'll get this term. So d by dt equal to dou by dou t plus u bar del dot. So which gives dou rho by dou t plus rho into del dot u bar equal to 0. This is the equation of continuity which we are going to use. Now equation of motion. The Euler equation of motion is given by dou u bar by dou t plus u bar dot del into u bar equal to minus 1 by rho del p plus f bar, where u bar is the fluid velocity, p is the pressure, and f is the external force, and rho is the density of the fluid. Now, actually, in our problem, there is no external force acting on the fluid, so we can eliminate this f from this Euler's equation. Okay, that will explain again. Okay, now let us come to the problem. Come to my problem here. Now we are taking the two rotating coaxial cylinders. Now we are considering the fluid in between these two. Okay, so this fluid is actually, it is having here, it is a incompressible invisible hydromagnetic non-homogeneous swirling flow in between two concentric coaxial cylinders, with the inner cylinder radius is r1 and outer cylinder radius is r2, with the angular velocities omega1 and omega2, that we are going to consider, and we are modeling the problem of this fluid of motion of the fluid. Now before going to start any problem, any modeling, okay, otherwise we will follow some few steps to model the motion of the fluid between two concentric cylinders here. Now first of all, we start with the initial flow which represents the stationary state of the system. Okay, now we will assume that the physical variables like velocity, pressure, which represents the flow, which disturb with a small increment, or there will be a small disturbance in the fluid wave velocities or fluid variables in a flow. Then there will be disturbance in the variables of variable represents the flow also. Okay. Now what we do first, we obtain the governing equations of the increment first. Okay. Then we obtain these equations relevant to the equation of motions, and this is the very important point, that after obtaining the equations governing the increments, now we'll neglect all the products and powers higher than the first. Means we are taking only, considering only the linear terms of increments. So means we are considering only linear terms of increments in the equation. So what we can say, the theory behind this is based on linear terms. It is called a linear equation. Is actually we are only considering the linear equations. So we can say the theory is called the linear stability theory. So we are taking only linear stability theory, means we are neglecting all the non-linear terms of the increments. Means we are neglecting all the products and higher powers than the first of the increments. Okay, and we are assuming that the increments or disturbances are very small. Disturbances, we can say perturbations, are very small. We can say infinitesimal. Okay, so this concept we can use to model the problem. Okay, now let us comes to my problem here. The stability of inviscid flow or under also incompressible hydromagnetic swirling flow in between the coaxial cylinders, and when the axial pressure gradient is present. Okay, axial pressure gradient means for del P. Pressure gradient means del P if it is present. Okay, now as we said that our fluid motion, which involves the two basic equations. One is the Euler momentum equation, one more is the equation of continuity. Now Euler momentum equation is given by this, and as I said before, here we have uh, this equation includes F bar external force also, but there is no external force acting on the fluid, so we eliminated this F bar. So we are using only this term for the equation of Euler moment equation. This is the equation 1, and we are going to express this Euler equation in terms of cylindrical polar coordinates r, theta, z. Okay, now equation of continuity, and where this u bar in cylindrical polar coordinates, it is represented by u r u theta u z, that is u r r cap u theta theta cap plus u z z cap, the velocity of the fluid. Okay, now equation of continuity, conservation mass, that is dou rho by dou t plus rho into del dot u bar equal to 0. Now since we are assuming, since the fluid is incompressible, incompressible means what, already we defined there, the fluid in which the density is constant are called incompressible fluids. Okay, so here the density rho is constant. If the rho is constant, this term become what, dou rho by dou t become what, 0. So we'll get only one term, that rho into del dot u bar equal to 0. So from the equation of continuity we are getting only one term, that rho del dot u bar equal to 0, since this term will become 0. Okay, this term will become 0. Okay, now since the rho is constant, so with non-zero constant, then we can write it as a del dot u bar equal to 0. So finally what we got now from the equation of continuity, we got only this term, del dot u bar equal to 0, that is equation 3. So finally we got two equations. One equation is Euler moment equation, this is one, and the next one is a del dot u bar equal to 0. Okay, now we are expressing these two equations in terms of cylindrical polar coordinates. Then we can write it as the first one, Euler equation. We can write it as the first one is dou u bar by dou t. This is the u bar. Okay, the next one is the u bar dot del. What is del here? Del is the gradient vector r cap dou by dou r plus 1 by r, theta cap dou by dou theta plus z cap dou by dou z. Now the remaining all we are expressing in terms of the cylindrical polar coordinates, so that the equation 1 become this equation. Then similarly, now let us simplify this equation. Now we'll do the we'll apply the derivatives, and also we'll do the dot product of these two. Then we'll get the next equation like this. Means see, dot product of these two, which gives u r dou by dou r plus u theta, means 1 by r u theta dou by dou theta. The next one u z dou by dou z of u bar. U bar is nothing but again same thing, velocity vector. Okay, so velocity vector, yes, we have written like this. Then we can operate this derivative with again u bar. Then what we'll get the next equation like this. So we are doing we are operating like a ur of dou by dou r of this total function, total velocity. Okay, then 1 by r u theta of dou by dou theta of again all these things. Okay, then what we'll get here, we'll get this equation. Now we are writing separately ur and u theta by r uz separately. Then now here, now what is actually r bar is the position vector. R bar is the position vector. If you take any point on the cylinder, now then r bar will be the position vector of this point. Then the angle between these two is theta. Then if you we can easily understand that the x gives the r cos theta from this, and this y gives the r sin theta, and z equal to only z. Okay, since the flow is only the disturbance will happen only through the x and y axis, so z will not change, so z equal to z only. And the unit vector r bar r cap defined like dou r bar by dou r by modulus of dou r by dou r. Similarly, theta cap z cap unit vectors defined like this. Now then using r bar, we can find the unit vectors like r cap equal to cos theta I bar plus I sin theta j bar j cap. Similarly, theta cap and z cap, we got it. These are the unit vectors we got from this r bar and x, y and z. If you are keeping all these things in this position, we'll get r bar. Then after finding the unit vectors, we'll get r cap, theta cap, z cap this way. Now, what are all the terms involved here in the previous expressions? Now here we have dou r by dou r, dou theta cap by dou r, dou z bar by dou r. These are all terms involved. Now anyway we got what is r cap. Then we are finding all the derivatives using this r cap, theta cap, and z cap. Means we are finding the partial derivative of this r cap with respect to r, theta, and z. Okay, so after getting these values, we are substituting in the previous equations, so that we'll get the new equations like this, new equation like this. Then now after simplifying the equation and comparing the each component, means there are three components r, theta, and z. If we compare the three components on both sides, we'll get three equations with r component, theta component, z component. Okay, these are the new equations which we get, and here we can observe that, okay, these are the new equations which we got it. Then now what those equations we got, previous equations we got from the Euler equation, and from the equation of continuity, what we get, that is del dot u bar equal to 0. This is del and dot u bar equal to 0, and again we operate this. Okay, we'll get rho r cap dou by dou r of this function, same 1 by r theta cap of dou by dou r of this one. Similarly, all these things will get. Now when you operate the derivative of this one with u bar, so we'll get the new equation like this. Now dou u r by dou r plus 1 by r u r, and this term will get. And since we observe that now there is a axisymmetric disturbance. Okay, means we are saying that the flows are axial flows. Axis means axisymmetric flow. Axisymmetric means what we said, the velocity and the pressure does not depends upon the angular coordinate theta. So this is u theta does not depends upon the variable theta. So we can say that the dou u theta by dou theta value become 0. So finally we'll get only three terms in the next equation, that is dou u r by dou r plus 1 by r u r plus dou u z by dou z equal to 0. This is the new equation which we got from the equation of continuity. So previously we have 3, and now we have this one 4. Okay, now